Hi everyone, welcome to Lecture 7P of Useful Genetics, where we're going to talk about relatedness. We'll talk about paternity testing first. This is a topic that really would have fit in our discussion of DNA fingerprinting, except that we hadn't really talked about inheritance yet, and it's hard to talk about paternity when you haven't yet really thought about inheritance. We'll then think about lots of levels of relatedness, not just parent and child, but siblings and aunts and uncles and grandparents and cousins and second cousins and third cousins, looking in each case at how much genetic sharing, what proportion of shared alleles is expected for each level of relationship. And then we're going to look at some real genome comparisons based on SNP typing analysis of family members that will let us see how real genomes compare to the ideal predictions of the theory. So here's a diagram from our discussion of DNA fingerprinting. And you'll remember that these colored blocks represent different alleles of 13 different VNTR loci, where VNTR stands for variable number tandem repeat. So we have 2 alleles of this locus in the father, 2 other alleles in the mother, 2 alleles of the second locus in the father, 2 alleles of the second locus in the mother. And from these, meiosis selects a random combination of the alleles in the 2 sets in the parents to pass to each child. And the consequence is every child has different combinations, but every child has one allele that's identical to an allele in the father, and one allele that's identical to an allele in the mother. Now, when this is applied in a paternity testing situation, here's how it works out. So the father's DNA is scored for which allele he has at each of the 13 VNTR loci. I've only shown 6 here. And the child is also scored. If the father is truly the father of the child, then at every locus, one of the child's alleles must match one of the father's alleles. So here, okay, the child's got 7 and 4, the father's got 7 and 5, so that allele matches. The child's got 6 and 4, the father's got 2 allele 4s, etc. And for true paternity, every allele must have a match. 5 and 5, 11 and 11. So provided this carried through for all 13 alleles, we would say, yes, this man is the father of this child. Now, here's another child. We can do the same analysis. 7, I'll do it in a different color. 7, yes. 4, yes. 6, yes. 3, yes. A 6 and a 7, uh-oh, no match. 13 and a 7, uh-oh, no match. Now, a certain number of matches are expected just by chance because these alleles are quite common in the population, and it's not unexpected for even unrelated individuals to have alleles in common. The test really works the other way. Having alleles in common doesn't prove that the man is the father. Failing to have alleles in common is very strong evidence that the man is not the father. Now, because VNTR loci mutate at a high rate relative to normal chromosomal genes, it's usually not considered sufficient that one of the 13 alleles doesn't match. One of the 13 loci doesn't have a match. It's usually required that at least 2 of the loci don't have a match in order to say definitively that the man is not the father of the child. So paternity testing won't prove absolutely that a man is the father of a child, but it can prove very, very high confidence that he is not the father. grandparents, well, I'm showing this diagram, which I've showed before, because I want to introduce one new term. I think it was obvious that I was using colors in this diagram to indicate relationships of sequences. So, for instance, this blue sequence would be a copy of that blue sequence, which is a copy of that blue sequence. And we would describe these sequences as being identical, and we would describe sequences in related individuals as being identical by descent. So this segment of this sequence is identical by descent to this blue segment in this other child. They both inherited it from a common ancestor, their father. So it's identical by descent. And we could trace it farther back. If we looked at cousins, we would find that cousins have some segments of their genomes in common that they inherited identical by descent from a grandparent. Now, on this slide, I've created a diagram showing the predicted levels of relatedness, the percent of alleles in the genome where two individuals are expected to be identical by descent. And these alleles will occur in segments of identical or very closely related sequence, as showed in the previous diagram. So the first value is for identical twins. I haven't shown them on the graph. Identical twins have identical alleles at all loci, so we would say they are 100% related. That's their level of genetic relatedness is 100%. Parent and child are 50% identical. That's because one of the child's two alleles is at every locus identical to one of the parent's alleles. And that's true for this parent. It's also true for this parent. The same level of relationship is seen for full siblings, but for different reasons, as you'll see in a few minutes. If we compare grandparent to grandchild here, or aunt or uncle to niece or nephew, we expect to see 25% identity. And if we compare cousins, we expect to see about 12.5% identity. Now you'll notice that each time we go down one generation on one side or the other of the tree, the relatedness drops by a factor of 2. So when we go from siblings to cousins, it drops by a factor of 4, a factor of 2 here, and a factor of 2 here. When we go down to second cousins, it'll drop by a further factor of 4. So second cousins only have about 3% of their alleles in common. Third cousins only have less than 1%, and fourth cousins only about 0.2%. Now, it's these third, fourth, and further cousins that are the relationships that 23andMe most commonly finds, because we all have many more third and fourth and fifth cousins than we have first or second cousins. Now let's look at some real genomes and see what real relatedness looks like. And I'll start by showing, what I'm going to show you are diagrams generated by 23andMe when members of different generations of the same family have had their DNA tested. 23andMe will compare any two individuals, but in this case, what they've compared is a parent and their child. And the color code is explained here. The gray segments are places where there's not enough information to type. Typically, this is places on the chromosome where there's a lot of repetitive DNA. And the blue bars are places where the two individuals are half identical, where they have one allele in common. And we see that between parent and child, they're half identical everywhere. And that's exactly what we expect, because the child's genome, one of its two copies of every gene, came from that parent. The other copy came from the other parent. So this is exactly what we would expect. Now let's look at a comparison between a grandfather and a grandchild. This is 2 generations. Now our clean blue lines are broken up into segments. So there are segments of the child's chromosome that are identical to segments of the grandfather's chromosome. And then there are other segments that are not identical. And these will be segments that are derived from the other grandparent. Rather than from the grandfather, they're derived from the grandmother. Again, the cross-hatched and gray segments are places where the DNA was not analyzed. Now, this pedigree, this diagram, we can interpret the boundaries between the blue and white segments as places where crossovers occurred in a meiosis, generating new connections between the grandmother and the grandfather's homologs. This question asks you, where did that meiosis happen? In which person was that meiosis?